Hey, okay, cool. It works this time. Um, do I have everything else set up? This is the problem with doing this is that sometimes I just don't know. Uh, but yep. I asked people if they wanted me to do this again. They said most of them said yes or were unsure that this had occurred before. So I'm doing it again. Um, and just move a few things around on the other screen really quick. Yeah, so um, hopefully I'll be able to get through more problems in full this time around than I did last time. Just because I need to know how to do these things, and I need to know how to do them efficiently. And the first problem that I'm supposed to do, well, the next problem on the list of problems is a pretty involved one, but it'll be fine. It'll happen. It'll be over. It'll be good. And I will either have to take this test again in January or I won't. So hope is that I won't. Oh, let's see. 50 that, and then brush. I guess yellow is a good color. Um, so this one's actually like a real analysis problem. Sort of, it feels like an analysis problem because this is one that's usually on analysis quals as well. But um, this is just for my own sanity. Where's that? Yeah, August 2021, which means I'm almost done with this test as well for in terms of like streaming purposes. Um, but so show that every uh, metric space can be isometrically embedded as a dense set of its completion. Well, I should be careful of a completion. So of a complete metric space. Metric space. And that, well, there's a few things. The resulting completion is unique up to isometry. Up to isometry and um, it fixes all points of M. Oh yeah, so brief problems that I'm overview of problems that I'm working on. This is like anything and everything that could be on my topology qual that is coming up in August. So I'm working through a series of tests. So for example, I'm not like I don't put the PDF on screen just because for I don't know if the department would be weird about test security, but I have a handful of tests um, that I'm working off of that are past topology qualifying exams for my institution. And where I go to the topology qualifying exam is usually over things that are in more of the point set topology realm than the algebraic topology realm. The closest thing that we get to any algebraic topology is stone check compactification, and even that is more so just like topology for its own sake and not really any algebra. So there isn't really any algebraic topology on this exam or in any of these problems. Um, there are also some problems that are like topological dynamics, and there's also a lot of metric space problems as well, because the committee for this exam, the people who grade it are, well, one person is a set theorist slash logician, the other person is a model theorist, and the third person, who is my advisor, is a topological dynamicist, um, or like does dynamics in general. He does a lot of stuff. He does a lot of stuff. But anyway, that should give you a brief idea of the different areas I will touch. A lot of these things are either like standard results in point set topology and in the theory of metric spaces, or they are applications of standard results in topology and point set topology in particular, and other areas. Hopefully that answers your question. But yeah, I'll just be hanging out doing problems, and then if people have questions or want to ask me things, feel free to just plug in chat, and I will address them as they come up and as I have space in between thoughts. So, okay. Okay, so show every metric space can be isometrically embedded as a dense subset of a complete metric space, and that the resulting completion is unique up to isometry. And what's the last part of this? Fix that fixes up to isometry. That fixes points in the metric space. So let's see. Let me give it a name. Every metric space M can be isometrically embedded as a dense subset of a complete metric space, and that the resulting completion is unique up to isometry that fixes points in M. Or rather, yeah. Yes. Which is a weird way of writing it, because you're not really fixing points in M, you're fixing points of the embedded image of M. But anyway, so this is like a pretty standard analysis problem as well, because when you do like analysis, you're working with several different metric spaces usually, whether those be your LP spaces or um, and whatnot. And so it's common to see this proved as part of an analysis class as well. Oh, the username. I've already okay. I'm just gonna read that as its opposite day. That's oh, but having homework due is never fun. Um, so okay, so I should probably write proof instead of prop. So proof. So this the natural place to go is like so complete metric spaces are where Cauchy sequences converge within the metric space. So in order to get a complete metric space out of a metric space that may not be complete is to just look at the Cauchy sequences. So consider the space M. I don't want to say M bar because M bar is closure. So like, I'm gonna write this. I guess little c of M. I don't think that's used anywhere. We're gonna go with it. So consider space C of M, which is equal to the set of sequences such that xn within n is Cauchy in M. And so what that means is that as you get farther out in this, there's a point, as you get farther out in the sequence, pairs of points that are far enough out in the sequence remain close together. So the consider space, blah, blah, blah. Anyway, so how does this work? We need to put a metric on the space. So and define D between, and I guess I want to write these in a different way. So I'm going to write these as like, how do I want to do this? I guess that's fine. It's okay. Yeah, it's okay. Because each of those things is, yeah. All right. So the distance between two sequences, and I'll just drop the indexes for now because they're all just the natural numbers, is going to be equal to the limit as n goes to infinity of the distance between xn and yn. So why does this work? So note that that's not right either. I don't want that. That doesn't make any sense. What I just wrote is I'm defining a distance. Yeah, so these two things are from my Cauchy space. This is the distance function, so it goes from the cross product. So this is cx plus cx. This is the distance function, and that will go to, and these are all real numbers. So this goes to r. Okay, so it's going to the right place. Yeah, scratch what I just doubted myself on. This is what I want. So, let's get rid of some negativity. Here we go. And then, awesome. Cool. Okay. So this is what I want. This is the distance function, and I just want to show that it works for a few reasons. So first, I need to acknowledge that this sequence is Cauchy in R. So note first that the distance between xn and yn, this sequence, and within the naturals is Cauchy in R standard. So what that means, so in particular, how do I show that that's the case? So given n and m large enough, I should also be clear here too. Right, so let m comma d be the metric space, or a metric space in question. So D is the metric, right? So we're Cauchy with respect to M, each of these xn and yn's, but then these evaluated distances, I want to show that the evaluated distances are also Cauchy, but in the real line. So given n and m large enough, consider d of x and ym. Well, this is d is a metric for m, so this is less than or equal to d of x and xm plus d of xm ym. Oh, yeah, this is fine. This is still okay. It's less than or equal to a distance between x and xm. So in the first step, I just put xm between xn and ym, and then in the next step, I'm going to put yn in between these two. So this will be the distance between yn, ym plus the distance between yn and xm. Um, and this is, how do I want to do this? Why is this weird? Oh yeah, no, this is fine. So then the distance between, I just made this way more complicated than it should be. I wanted to consider the distance between um, minus distance between xm, ym. That's what I wanted to look at. Part of this is me screwing up because this is how it's going to be on the test itself, is because I'm not going to be like, I have notes in the event that I like get totally stuck. So for the most part, I'm doing this just off the cuff. And then if I get so stuck that I have nothing to say, I have notes to fall back on. But during the test, this is how it usually goes when I take exams, where I like say something, I like write down something, and then it's like, that's just blatantly wrong, and then have to correct it. So I want to show that this thing is Cauchy, so I need to look at the nth thing and the mth thing for large enough n and m. Well, this is just xm, ym, and then so I'm going to put xm in between these two and yn in between these two, so this will be less than or equal to the distance between xn. Oh, but then I have to be weird about the subtraction, because I can't make both of them bigger. It's the only thing. Oh, I know how to do this. Okay, so distance between xn and xm plus the distance between, oh, but then it's also weird, right? Both of these numbers are positive, so I don't really need well, so then the absolute value is just, well, whichever one's larger. So whichever one's larger, so can I assume that? I can assume that one of them is larger than the other because there's just two of them. And that will always happen. So without loss of generality, let the distance between xn and yn be greater than the distance between xm and ym, then I can do what I want. Right, if not, then I can just switch the places in the absolute value and we're still okay. So then this is less than or equal to the distance between xn and xm plus the distance between xm and yn minus the distance between xm and ym. And then this is less than or equal to oh, that is weird. This should not be hard. This is like basic analysis, Nathan. We've passed this qual already. We should know how to do this. I have it written. I have something false written down, but I just want to say that this is a Cauchy sequence. Because I want to apply it to the negative stuff, but the negative stuff you would be making that negative stuff larger, which is the problem. So maybe I should go back to what I was doing before. I just need to show that it's like an epsilon over 2 plus epsilon over 2 thing, where this is why we do this. This is why we do this. So it happens now and not when you're sitting and stressed in an 8-hour test. Ooh, that rhymed. Okay, because I want to replace this with minus d of xm Well, I don't think I can do that. I don't think I can do that. But yeah, I can't do that because the middle things will cancel and that won't make any sense. So if I just look at one part of it, it'll be, I don't want to consider the difference outright. Let's just look at the distance between two things. This also might be one of those days where I just like can't do it. uh, which happens. That's a thing that happens sometimes. You just, especially when studying for the test and having studied for it for so long, there are instances where I get up in the morning and I sit down to do a problem and I just can't. Just nothing, nothing comes out up here at all. It's really frustrating sometimes, but it is what it is. So, okay, so given n and m large enough, consider I'm just gonna consider distance between x n and y n, and so the distance between x n and y n is less than or equal to the distance between x n x m plus the distance between x m y n, which is less than or equal to the distance between x n x m plus the distance between y n or y m yn plus the distance between xm and ym, which is, so that means that the distance between xn and yn minus the distance between xm and ym is less than or equal to this distance. Oh, that's not what I wanted to write. Oh, okay. I was doing it right the first time. My notes are wrong, which is fun. I'll fix those too. Great. That was great. Yn. And so then letting, and then this thing is, so this is always positive. So, oh, but I can't say that either. Mm. Oh, and then similarly, okay, this is fine. This is okay. So similarly, distance between xm and ym is less than or equal to the distance between xn xm plus distance ym plus the distance between xn and yn, which implies that the distance between xm ym minus the distance between xn and yn is also less than or equal to xn xm plus distance between ym and yn. So it's just using the triangle inequality on the same stuff. And so then that just gives me that these two things tell me that the absolute value of distance between xn and yn and distance between xm yn or m is less than or equal to the distance between x and xm plus the distance between ym and yn. And then letting n within n large enough such that for every n and m greater than n, the distance between xn and xm and the distance between is less than epsilon over 2, and the distance between ym and yn less than epsilon over 2, we get that this thing is less than epsilon. So this thing works. So this thing is Cauchy. So this implies that the sequence of distances is Cauchy. and hence converges. So, right, so this whole thing was just to say that this function that I've defined here makes sense. So, so hence, the distance between two sequences is, it will exist, right? So, and is well defined. Which I know that's not what an algebraist would say was is well defined, but this is where I'm at. Um, this is so that thing exists and is well defined, and then well, I want to show that D is a metric. So is it? So note that D is a metric since if xn, well, so, oh, it's not a metric. It's not a metric. Lies. Um, there is an equivalence relation that I'm missing because it's not that it's just Cauchy sequences, it's that you want the Cauchy sequences that converge to the same thing. Right? Then does that make sense? Hold up. Where did we write down? Oh yeah. Okay. It's under the equivalence relation if the limit under, yeah, so then yeah, there is an equivalence relation at play here. So I can't look at just the Cauchy sequences to make this a distance. This would be a semi-metric, or in this case, because you could get things that are zero distance apart that are not equal. But in order to force it to be a metric, I just make all of those things equal to each other. So so to make D a metric, we further define we define uh, equivalence relation on how do you define equivalence relation? How do you write that said theoretically? It's just you have an equivalence relation, um, and it's going to, well, what does it do? Um, it is a subset of the Cauchy sequences crossed with themselves, such that um, x is related to y if and only if the limit then goes to infinity of the distance between xn and yn is equal to 0. Then, well, this tilde is an equivalence relation. Which I don't want to write all the details out for that because I think that's getting too granular for a qual problem. Um, so the reason that it's an equivalence relation, right, is that if the relation is symmetric because, or is reflexive because if you have the same sequence, then this limit will be equal to 0, so you're good. It's symmetric because if you switch the orders of the x and y, right, the distance function doesn't change, and so then you'll get 0 still, and then it's transitive because if one limit is equal to 0 and the other limit is equal to 0, then the first compared with the third. So if you have, right, so I guess transitivity is the only non-trivial thing. So let's do that. So transitivity of true is the only non-trivial argument, or well, the only non-straightforward. It's straightforward. It's just I'm using the word I hate. I don't like saying things are trivial because they're not trivial to other people, and so it's like a whole. It's like it's one of those things where it's like not a great word because it's has a just like a pompous connotation to it, and I don't like using it. So transitivity of tilde is the only part of the equivalence relation argument. Argument that is not immediate. So suppose x is related to y and y is related to z, then right, and again, this is a sequence of stuff. These things are sequences, so the limit as n goes to infinity of distance between xn and cn can be less than or equal to the limit as n goes to infinity of the sum of these two things, which is equal to 0, but this is a limit of non-negative numbers because distances are not negative. So this implies the distance between x and, or the limit of the distances x and cn is equal to 0. Hence, so we propose that D is a metric on C of M mod tilde. So if, in particular, D of X, so I don't need to write it that way either because that's super confusing. So xn and yn is equal to 0 if and only if the limit as n goes to infinity of the distances of xn, or of xn and yn is equal to 0, and that just means that they're equal by the definition of tilde. So x n with an n is related to yn with an n, which is if and only if x with an n, this equivalence relation, or this equivalence class is equal to the equivalence class of these sequences, which is what it means to be equal in this quotient space. And then, oh gosh. So that's the 0 property, triangle inequality. I need triangle inequality and symmetry. So it's symmetric, so that's by definition. So D is symmetric by properties. I guess symmetric and has the triangle inequality by properties of D, the original metric, because the original metric has symmetry and the triangle inequality. So I can just do a similar thing to this as I did above. So we're good, and D is a metric. So D is a metric. D is a metric on the Cauchy sequences modded this equivalence relation. Okay, so now I'm working in the space of things that are the candidates to be the complete metric space. So what do I need to show? I just need to show that every metric space M can be isometrically embedded as a dense subset of a complete metric space. So I have that I can isometrically embed now because I could just go ahead and define a map between the metric space M and this modded Cauchy sequence space. So define um, phi from M to C of M mod tilde by phi of X is just going to be equal to the equivalence class related to the constant sequence of just X tilde. So this is just the constant sequence. Then the distance between X and Y, well, for every Y with an M, the distance between X and Y is equal to the limit as n goes to infinity of the distance between X and Y, which is equal to the limit as n goes to infinity, right? Because the limit doesn't affect a constant. So you have the limit as n goes to infinity of the distance of each term in this sequence, which is just this is equal to the distance between well, the constant sequences in their equivalence classes, right? So I guess I can just get rid of that for now. And then that's just equal to the distance between phi of X, because this is I'm abusing notation for sure, but that's so uh, that's okay. Eh, you know, this is math. This is what I do. So I enjoy it. You might be very confused or just have no idea what's going on. I sometimes also don't have know what's going on. So it is what it is. Uh, okay, so that gives you the isometric um, embedding, right? Because so this map is obviously bijective um, because if you have a sequence that's just a constant sequence, you can pull it back to just what thing is in the constant sequence, um, and you can also go forward to the constant sequence in a nice way. So note that phi is bijective and isometric. Well, is I guess is an isometry always bijective? Oh, yes and no. I don't know, like I don't know how deep to go, but like also I am doing problems at a certain level, so it's kind of it's some stuff is like hard to get to the granular stuff after you without like going down the ladder of like this is what this means, this is what this means, this thing implies this and blah and doing that descent. Um, so so note that phi is an isometry. So I guess I proved that phi was an isometry. So phi is bijective and distance preserving. So it is an isometry. I think that's what I want to say. I just want to double check the definition of isometry because I think I'm saying it wrong. Um, yeah, so an isometry is a distance preserving transformation between metric spaces, which is usually assumed to be bijective. Oh, wonderful. And it has this nice picture. I didn't mean to make it that huge. I just wanted to make it small. There we go. Okay. It's got this nice little picture. which is so fun. Um, which, if I spent enough time looking at it, I could explain it. But right now, I'm not in that headspace. Um, and so the picture is a composition of two opposite isometries. It's a direct isometry. A reflection in a line is an opposite isometry, like R1, R2. It's a direct isometry. Okay, so this is just like a difference between rigid motion and um so rigid, yeah, okay. Because rigid motion like preserves like relative. Okay. Anyway, that's an aside. We cannot focus on that forever. It's distance preserving, so it's an isometry, and it is a proper subset, and phi of M is definitely a subset of that space because you're embedding it. Um, so so I guess the picture for this is that you had M and there's this space of Cauchy sequences, and I made M hang out in there, and now I just need to make sure that it's dense and whatnot. So uh, for density, do I want to do that right now? Or do I want to do something else? So yeah, let's do density. So so it's isometrically embedded for density. Um, it's a metric space, so I just need to look at a ball. So so for some sequence y sub n, which is a so it's within C of m mod tilde, within naturals, and an epsilon greater than 0 given um, there exists, these are Cauchy sequences in M. So there exists a big N within the naturals such that the distance in M between ym and yn is less than epsilon for every m and n within the naturals. Great, such that, well, it's for every m and n greater than or equal to big N. So the sequence, so the sequence, the constant sequence zk for n within, or I guess yk, um, n within n. So again, so k and n are not related. It's just that this is in C of m tilde, the constant sequence with yk is some point within the original sequence that we started with in the general Cauchy space. Um, and k is going to be greater than or equal to big N is such that the distance, the distance between yk and yn is less than epsilon for every epsilon, or not for every epsilon, for every n greater than or equal to big N. So the limit as n goes to infinity of the distance between yk and yn is going to be less than epsilon as well. So I guess I should be a little bit more careful there. I should say, okay, so there gets this an n greater than zero, great, because the limit could be like approaching epsilon from above. So it would be an epsilon greater than zero given there exists an n with an n such that the distance between, so you go far enough out in the Cauchy sequence that you can get epsilon over 2 close together. And then for every, you have the constant sequence, and that'll be less than epsilon over 2. So this will be less than or equal to epsilon over 2, but that's strictly less than epsilon. Hence, um, uh, the image of the metric space, so phi m, intersect the ball with respect to the distance big D um, of some sequence, some arbitrary sequence, yn, and within the naturals, and some epsilon given that's greater than 0 does not equal the empty set. So as yn, n within n, and epsilon arbitrary, phi of m is dense in C of m mod tilde. Okay, so that's the first half of the problem. So I showed that, oh, okay. So I showed that any given metric space can be isometrically embedded as a dense subset of a complete metric space. Oh, I didn't show that completely, did I? I didn't show that this was complete. I need to show that the Cauchy sequences, the space of Cauchy sequences is complete under this modded, under this equivalence relation. So that's the last part. Almost there. So it is dense in this modded space. And then lastly, we claim that C of m mod tilde is complete. So this is where Cauchy sequences converge. So, oh. So Cauchy sequences converge is what I want to show. So how does this work? I guess I want to say, let's do it this way. So let's let x to the n denote some sequence of things within, be a subset of these Cauchy sequences be a Cauchy sequence of these equated Cauchy sequences, then, well, that just means we have that the distance between, well, for some, well, yeah, so for epsilon greater than 0 given, there exists an n within the naturals such that for every m and n greater than or equal to n, the distance between xn and xm is less than epsilon. Which means that, oh, there's some weirdness to address here. So then, okay. So this goes to, or this implies that limit as n goes to or I'm going to use k because I've already got n and m hanging out. So k goes to infinity of well, what's the definition of big D? Well, it's the distance on the m metric. K, m, k is less than epsilon. And so this is an isometry. B is an isometry, but that doesn't help. I want to claim that this converges to something. I just don't know what I want to claim that it converges to. Oh, I'm stuck. This is great. Okay. Um, I was saying Gaussians are given there because it's a big N within the natural, such that for every m and n greater than n, the xn sequence distance between those two sequences is less than epsilon, which means that the limit as k goes to infinity of those distances is less than epsilon. Which means that for every, I can do like a weaving of the sequence. But I don't think that's what I want to do. Or is it like a diagonal thing? I think it's a diagonal thing. Where, okay, so this is what's happening in my brain right now. So I have two sequences. Where I have a Cauchy sequence of sequences. So I've got okay, change color. I got like x11, x12, x13, blah blah blah, and x21, x22, x23, 2, x31, x32, x33, and so forth, and that goes down, and that goes down, and that goes down. And so this is what xn within the naturals subset of cm tilde sort of looks like. It's a little bit weird because these are all equivalence classes, but that's fine. It's not super crazy to have that be the case. And these are Cauchy sequences. The Cauchy sequences, and they are, as we get far enough down, they're getting closer and closer together. So if I look at the, I guess I want to look at this sequence. That's what my gut says to do. So that's going to be Cauchy. I should have written this in a more to mirror what I've been doing. This will be, so it's the first sequence in the first place, first sequence, second place, first sequence, third place, second sequence, first place, second sequence, second place, second sequence, third place, third sequence, first, third sequence, second, third sequence, third, down the line. So I guess, consider the diagonal sequence x n n. and within the naturals, this, and then the claim is that I need to show that this is Cauchy. So, so then the distance, we claim that, I guess I'll call this, I don't want to use that. Yeah, I'll just write it again. It's one of those things where it's like the notation gets so clunky that I just want to make it a shorter thing, but I've already committed to it being clunky. So you've got this, we claim that this sequence is within CM tilde, and that this Cauchy sequence converges to, or this sequence of Cauchy sequences converges to that diagonal sequence is what I want to say, and I'm not sure. It's not. I feel like this is the right thing to do, but because the common thing when you have a sequences, you have a sequence of sequences. It's common to look at the diagonal as one of the places to start if you're not sure what to do, and so I am doing the thing. Okay, so I need to show that it's in the space. So consider consider the distance between xn and xm. And so this is going to just be hello. And so this is just going to be less than or equal to the distance between xn over n. Oh, this is the same thing I did earlier, I think. It's the same distance style argument from above, way up here. Where I do something like this, I think is what happens. So because I know they're all Cauchy. All these sequences are Cauchy, and then it's Cauchy of Cauchy. So I need to use the Cauchiness of each individual sequence. So I need to go to like xnm plus the distance between xn n or nm xm m, and then this is going to be less than or equal to. So now this thing is Cauchy, and I know that the overall distance between yeah, okay, I think this will be fine. So this is less than or equal to the distance between xn and xnm plus the distance between the nn and m. I need to get oh, hold up a minute. Did I do that? Did I totally screw this up? Oh, why did I do that? Oh, that's an R. Okay. Oh, okay, that's fine. That's okay. Here is still weird. So I want to show that I want this distance to be less than epsilon for some given epsilon greater than 0 and n large enough. So I have nm, mm, so I want this to be x, n, m, and the thing I want to put between it is x, m, n. Or do I just want to... plus the distance between x, m, n, x, m, m. Okay, so this is like it's the nth sequence, nth term, nth sequence, nth term. Which is still okay because we're in Cauchy sequence of Cauchy sequences. So this okay, I can make small. Each one of these things is a Cauchy sequence. So for epsilon greater than 0 given, let n1 so I guess yeah, let n equal to the max of n1, n2, n3 large enough such that for every n and m greater than n1, the distance between x and n, x and m, that's less than epsilon over 3, and this exists since, so n1 exists since x n Cauchy. And then we do that the same thing for the m stuff, right? So then this will be the distance between, then for every n m greater than n2, the distance between x m, n, and x m m is less than epsilon over 3. There's some weirdness happening here. I don't think this works. Oh, this is that you can embed any metric space isometrically into a completion of itself, and that you can do so dense, such that the embedding is dense, and that all the way up top. Yeah, so show that every metric space M can be isometrically embedded as a dense subset of a complete metric space, and that the resulting completion is unique up to isometry, and that fixes points in M. So I've done that it can be isometrically embedded as a dense subset, but I haven't shown that the resulting space is complete. That is what I'm working on right now. So this is greater than n2, distance between x, so this I'm not, oh, well, I can do this for every, so this is weird because you're indexing on multiple things. So I don't feel like this works. And N and M, so if I just, maybe I should not be reusing N and M, but I am using the diagonal sequence. So I do need to have them be the same. So they're all Cauchy sequences. This is sketch. This is sketchy, I think. Any Cauchy sequence, X choose. Okay, I have to look at my notes because I am totally just butchering this, I think. Okay, I pulled from the wrong place. That's why this sucks. So instead of, so where's the issue? So we claim that this thing is complete. However, I need to be careful about what I'm working with because it's not straightforward to look at um, this thing in particular. So let me move some stuff because it's not all not salvageable. It's just I made a stupid mistake. So let's just pull you. That. Okay. So then let's move that down. Let me move it. Let me move it. Let me move it. There we go. So we since so since phi of m is dense in C of m tilde, we need only show that the image of M is complete as a dense subset, as a metric space with a dense, it's a metric space with a dense complete subset is complete. Subset is complete. So let this thing not be a subset of the whole space, but let it be a subset of the dense subset, the Cauchy sequence of the dense subset. Then we can have that for every epsilon greater than 0 there exists an n such that for every m and n, uh, these things are less than epsilon, so these things are less than epsilon. Then these things are a lot easier to keep track of because they are all just constant sequences. So instead of it being like x1, x, so it just looks like this essentially, which means now I'm not double indexing things, which is great. Um, so consider the diagonal. So yeah, so because they're Cauchy with respect to epsilon, and they're all just constant sequences, right? So I can rewrite this as like okay, so the diagonal is going to be Cauchy. That's not hard to show. So the diagonal, since each xn is constant, and the limit as n goes to infinity of the distance of xn x, or this should be k, xn xm. So, right, so these are the k things. Well, that's going to just be equal to the limit as k goes to infinity of whatever that thing was, right? So it doesn't actually matter what that thing was. So I can pick the first one because they're all constant sequences. And this will be less than epsilon, but that just means that the distance between x1 and xn1 and xm1, that doesn't make sense either. I don't want to say that. That feels wrong. Distance between these two things, the k is, they're all constant, so the distances between any two things that are apart go down. They're gonna get closer and closer together. Oh yeah, no, this is fine. This is okay. It's less than epsilon. So the sequence, get x of n is equal to x of n1, right? So this diagonal sequence is in the Cauchy sequence. It's not constant, right? So it's something else. And I also messed up this statement. We can only show that phi m is Cauchy sequences and phi m converge. So it's gonna be the dense subset where my analysis knowledge is just not happening today. And this is a longer problem too, which is frustrating. So it's okay. I mean, you only show that phi of m is or that Cauchy sequences in phi m converge. Converge in C of m tilde, since a dense, so since there isn't like a really nice way to say it. It's a dense subset, since a metric space with with a dense subset such that Cauchy sequences converge in the metric space is complete. Okay, so then that makes more sense. Then so we have our dense subset, they're all constant sequences. So if you look at a Cauchy sequence of that dense subset, then I can look at the diagonal sequence, which is going to be non-constant, possibly, but it is also Cauchy. So I can get rid of all of this stuff now. So So the diagonal sequence, so x n is within cm tilde, and we claim that and um, do I have anything else to say about this? Yeah, so consider um, so then the distance between the limit as k goes to infinity of the kth sequence with the diagonals, a match in the diagonal sequence. So x to the k and the sequence xn n naturals. This is the distance of that thing. Well, that's going to be equal to the limit as k goes to infinity, the limit as n goes to infinity. Goes clearer. So n to infinity of distance k n and x n n. Well, um, this thing will be should be 0. Why is it 0? Is it so? Okay, so the distance between so okay, so this is diagonal. These are all constant sequences, so I can replace the n here with a 1. Um, and then that means also that I can replace it with whatever this index is here. So I can always just make this n. Oh no, this is not great because it's a double sequence. I hate double sequences. I just want this to be 0. All I want out of life. Um, uh, another way to write this. So this thing, I guess the other way to write it is that this is phi of. That's not a great way to write it either, because it is a constant sequence. Do I need to do some? Oh, I can't do. Well, I don't want to do that either, because I don't want to put stuff in between. Um, so Okay, so this is just the first thing, and you run the limit as n goes to infinity first. Well, this distance gets arbitrarily small, but I can put stuff between it, right? Infinity of the distance between xk1 and xn1. That's just some constant, and then I have the nth thing. And so then this will be this sequence, this sequence of stuff is only dependent on because these are Cauchy, so the distances are Cauchy sequences in R. And so no matter what, wait, hold up. So if I go back up here, take a look at the thing, because this might make it clear to me. Uh, okay, so if you have two Cauchy sequences, and you look at the distances between those two things, it's Cauchy in R standard. So I have the distance between two Cauchy sequences. Um, the distance between two Cauchy sequences. So this is a Cauchy sequence, which is a constant sequence. This is another Cauchy sequence, which we just showed was a Cauchy sequence. Um, so this sequence d of x1 k x n n is Cauchy in our standard. And so our standard is complete. So that converges. So this thing converges to a limit. So the distance of x1 k xn n converges to a number, which I'm going to call epsilon star, within our STD. However, I know that if k is large enough, for k large enough, I can make it less than that epsilon. Um, so here's how that works. Okay, I think I know what to do. So and I just erased it, and now I don't. So sad. Okay, so you have this sequence of distances, um, x n n is Cauchy in R for all k within the naturals, because it's a sequence of distances between the elements of two Cauchy sequences, which I showed earlier was Cauchy in our standard. So these things converge to a point. Or rather, I just need to. So since our standard is complete, uh, these things converge. I'm going to call it epsilon k for every k in the naturals. So this sequence of stuff as n goes to infinity converges to some number within the real numbers for every k within the naturals. So I just want to make sure that that's zero, essentially. So, however, for k large enough, however, well, ooh, okay. But I can make k big. And if I make k big, then the constant sequences get arbitrarily close together. Uh, however, for a fixed k, um, there exists in big N greater than, or big N within the naturals, such that for every M and L greater than big N, the distance between x1 of and x L1, this thing is less than epsilon k, um, which implies that the distance between x m1 and but now I'm fixing k. Doesn't make sense. This is totally a mess. I know that this converges to zero. I am having a problem justifying it, which is great. It's one of those days where I just can't do it. It's oh, um, which I said about what, an hour ago? It feels like I've been doing this for a while. Can I tell? Yeah, I've been doing this problem for way too long, is where I'm at right now with this one, which is sad, because I should know how to do this by now. Um, okay. So it's complete. So this thing converges. Suppose it's not zero, but I mean it could not be zero. It's just why is this hard for a fixed n? Um, so if I fix, okay, let's just get rid of the limit for a second. Let's just get rid of the limit. Let's get rid of the double limit and look at one thing. So if I look at the distance between xk and its diagonal sequence, that's equal to the limit as n goes to infinity of the distance between xk, well, n and x n n, and well, that's going to be as n goes to infinity, this thing always stays the same. This is constant. And this thing becomes large. or well, not large, but it gets closer and closer to larger things. So um, if k is large enough, so if k is large enough, the limit for a given epsilon greater than 0. Okay, for a given epsilon greater than 0, let's start there. Do the analysis thing. For epsilon greater than 0 given, uh, as the sequences of Cauchy, the Cauchy sequence of Cauchy sequences is Cauchy. Well, that's, yeah. So for epsilon greater than 0 given, and k large enough, as this sequence is Cauchy. So x n and within naturals subset of b of m is Cauchy. We have that the limit, this is equal to, this is the limit of these distance, so limit d of x k n x n n is less than epsilon. And so then, since I can do this for any epsilon given, then if the limit as k goes to infinity, okay, so in particular, this making this small is independent of n as long as I start with k large enough. So if I start with k large enough, I will force so if I force k large enough, I will force the limit to be small because I care about going far out and n. So n will already be forced to be large by the limit, and I just need to start with a large enough k to get it small as possible. But then when I make that k bigger, it's also going to be less than epsilon. So then the limit k goes to infinity, the distance of x of k, x of n, n, oh, x n n is equal to the limit as k goes to infinity of the limit as n goes to infinity of d of xk of n xk or xnn. And this is just less than the limit as k goes to infinity of epsilon, which is just equal to epsilon. But I can do that for any epsilon greater than 0. But epsilon greater than 0 is arbitrary. So the limit as k goes to infinity of the distance between xk, xn, n is equal to 0. Hence, this sequence of sequences converges to the diagonal sequence. Okay, I think that's fine. It's something I will read over again, but that is what I'm going with right now. I am not a doctor. Do not call me doctor. I haven't earned that yet. So that is not my title yet. So but I appreciate that you enjoy what I do. Anything else? Ooh, there's a lot of random stuff here. It doesn't No, so you're so I guess the logic there is a little bit cyclic. So yeah, so for any metric space M, it is possible to construct a complete metric space which contains M as a dense subspace. That is what I'm proving. So, um, this is this is not something I can just take for granted. Um, okay. All right. So in particular, so in particular, um, Cauchy sequences in phi of M converge in C of M tilde, hence C of M tilde is complete. And I should probably just go through and approve that too, because the rest of this was a mess. So I should do the other this little statement too. That is let um, xn and within the natural subset of C of M tilde be a Cauchy sequence. So then we can go ahead and look at some thing in the dense subset. So we can choose a y sub m within v of um, m, such that I guess I just want to do y sub n. So I can choose a y sub n within phi of m such that the distance between xn and yn is less than 1 over n. For every n with the naturals, I can do this. So then for every n within the naturals, choose the stuff, which is less than 1 over n. And then the set y m is Cauchy. Is Cauchy. So the distance between xn and xm, well, that's just equal to, or that's less than or equal to, and then triangle inequality, because I showed that this was a distance metric, or well, this was a metric on the modded out Cauchy sequence space. So this will be distance between xn and yn plus the distance between yn and xm, which is then less than or equal to the distance between x and yn plus the distance between ym and xm plus the distance between yn and ym. And this is equal to, yeah, that's what I want to say. And this is just 1 over n plus 1 over m plus the distance between yn and ym. So taking taking n greater than n and m greater than 3 over epsilon, and the distance between yn and ym less than epsilon over 3 for some nm greater than or equal to big N and large enough for the given epsilon over 3 greater than 0. We have that since ym converges to y for some y within cm tilde, the distance between how does this work? It's the distance between xm and y is going to be less than or equal to the distance between xm and ym plus the distance between ym and y, which is less than 1 over m plus the distance between ym and y. And then this thing goes to 0 as m goes to infinity. Oh, hold up. I don't know why I did this part. This part feels unrelated. So this thing here, the coach students, that's fine because I need that. But then, oh, okay. Yeah, that's okay. So this is just showing that this thing is Cauchy. Because I want to take is that right? I don't think I need this. I don't think I need this. Okay, such that distance between x. This was a mess of a problem, and I'm still not done. Great. Okay, so hence xm converges to y as well, and thus cm mod tilde is complete. Oh, so up to unique up to isometry and fixes points of. There's got to be a nicer way to do this. So uniqueness is you just suppose that you have two things. And I'm just gonna go off notes now because I have been doing this problem for too long. Or maybe I shouldn't do this. This is, you know what? How we doing? How we doing? Yeah, we're taking a little bit too long. That's okay. It could be worse. What was the problem? All the way up here. It's been a while. I've been spending way too much time on it, but show that every metric space M can be isometrically embedded as a dense subset of a complete metric space and that the resulting completion is unique up to isometry that fixes points in M. So far, I have done the first half, which is that every metric space M can be isometrically embedded as a dense subset of a complete metric space. The next part is just show that it's unique up to isometry. So that is the where I'm at right now. And it should be fine. It just gotta finish it in this little tiny space. That's the goal. Finish it in the tiny space. So I have it that it's now we show that the completion is unique to isometry. So let x bar and x star be completions of x, or I guess I was using m, so I should stick with m. So m bar and m star be completions of m. Define then or okay, yeah, with m isometrically embedded by h, which will go from m into m bar, and g, which will go from m into m star. Then basically there's a diagram here, right? So it's I've got the following thing. So I have m, and I can embed it into its image. So okay, so we have m, and that goes into h of m, and then m goes into g of m, and this is a subset of m bar, and this is a subset of m star. So the goal is to then show that I can connect these things in the natural way. So consider f, which is going to go from h of m to g of m by such that f is like the natural thing. So this is by definition going to be equal to g of the inverse of h. So it's going this way. This will be inverse, and then g. The reason I can do this is because they're embedding, so they're one-to-one, or they're bijective. So I have inverses, so I can do inverses nicely. And since f is a composition of isometries, it's an isometry. So f is an isometry. As h and g are both isometries. So we consider some sequence for any y within m bar, a sequence of yn's subset of h of m, a sequence such that yn goes to y, which exists because of what was proven above. Do I have algebraic topology in my quals? I do not. So the last time algebraic topology came up in qualifying exams for my institution was actually in the algebra quals, and it was like 10 or so years ago, or at least, or like maybe 6 or 7 years ago at the earliest. But the topology quals majorly points at topology and dynamics. It's so some topological dynamics stuff and whatchamacallit, points of topology, topological dynamics, and then topology metric spaces, because the people on the committee are those are their like research. Oh, well, that's the stuff most closely related to those folks on the committee's research areas. Well, I like it, so it is what it is. So do sequences that yn goes to y, and that is my area of interest for research. So that's what I'm working to do. I have quals in 11 days. Yeah, it is a struggle. It's the I think it's the least healthy thing I have done in my life is prepare for a qualifying exam. So, ooh, n goes to y. Then yn is Cauchy, as it's in a complete metric space, and so is f of the sequence of the fyns. And this is going to be a subset of G of M. So let C equal to the limit as n goes to infinity of these fyns, and let yn prime go to y. Oh, why am I doing this? I just want to look at a different sequence that goes to y. Oh, I'm just showing that you can extend. Okay, that's, yeah. So if I have two different things that I have two different sequences that converge to this y within the completion of the metric space, if I can show that they, if I map them over and they go to the same place, then I can extend f from being a map on the dense images of the metric, the dense embeddings of the metric space and their completion to the whole completion. So then the distance between um, yn and yn prime goes to 0 as n goes to infinity, because they converge to the same place. And then we define, and the distance between z and f of yn prime is going to be equal to, or rather less than or equal to, the distance between z and f of yn plus the distance between fyn and fyn prime. And f is an isometry, so this is equal to the distance between z and fyn plus the distance between yn plus, or rather yn prime, and this thing will go to 0, and then this thing just goes to 0 as well, because z is defined to be the limit, which I can do because we're in a complete metric space. So this is going to equal to, or this is going to approach 0 as n goes to infinity. So so the limit, so z is, or rather, yeah, the limit, this limit is unique, which I guess is, we already knew that. Did we already knew that? Hence, okay, so f may be extended as a function k from m bar to m star in the following way. So it's gonna be k of y is just gonna be equal to c, where for yn converging to y, f of yn converges to z. And so the stuff that I just did shows that this k is well defined, right? Because if you take two different sequences that converge to y, then you're going to get two different sequences that both converge to z. Then k restricted to h of m is just equal to f. Oh, k restricted to h of m is just equal to f. And then the last thing to show is that k is an isometry. So, and to see that k is an isometry, okay, well, yeah, so, and it fixes, hold up. Do I need to say anything else about this thing? Let's go all the way back up. You look up the isometry that fixes points in M. Yeah, we're good there. Okay. Because so fixing points thing comes from earlier, because we're going between embeddings. So we're fixing points in M in that sense. And it's a more of a categorical sense than a point set sense that we're fixing the points in M's, because we're defining K based off of embeddings of M. So K is going to fix points in M because it's just what F is. I'm going to see that K is an isometry for Tn converging to Y within M bar, and Tn prime converging to Z within M bar. The distance between, and then these things are, right, where yn, and then this is going to be yn is a subset of h of m. Okay, so then with tn prime subsets of h of m, we have that. Hello, how's it going? We have that the distance between k of y and k of y prime, well, that's just equal to the limit as n goes to infinity of the distances between f of tn and f of tn prime, which is equal to the limit as n goes to infinity of the distance between tn and tn prime, because f is an isometry, and this is just equal to the distance between y and z. So I need this to be z, because that's what it was. It was not y prime. I did not define a y prime. I defined a z. So it's an isometry. It fixes points in M. I can stop talking about this problem now. Thank God. Okay, ooh, all right. So, oh, cool. You're from Peru. That's great. Um, okay. So that was a little much. Um, should have not taken me that long to do that problem. But here we are. Oh yeah. I need to do another one. I can't just do something about metric spaces and then just call it quits because it took me too long to do it. That's not how qual studying works. Quals are demand all of the time, all the time. Um, okay. But do I want to do something that's a mess, or do I want to just do something straightforward? I guess I should do something that's a mess. Um, path components. Uh, keep everything organized so I don't lose my. I'm trying to at least. Okay, that one was done. Took way too long. And then next one. Okay, so I guess I can do the line now since we're. I don't expect this next one to take me this long, but you know, you never know. The next one is going to be like a path component problem, I think. At least, yeah, path components of a space are equivalent classes up to the equivalence relation. And then, oh, there's two parts to it. What are the two parts? So the following statements hold: the path components of X are path connected and contain a connected component, and then if X is locally path connected, if and only if each path component of each open set is open. Um, okay, let me just write that one more time. August 2021, number 12, and then I can be done with this test. Well, at least this particular test. This is the last problem on this particular test. So the path components of a space X are the equivalence classes that's not even legible. um, under the equivalence relation x is equivalent to y if and only if there exists a path with it, which is a function, just a function from 0 to 1. I'm not going to get specific because the proof is easier if I'm not that specific. So as a path um, from x to y. So then prop A isn't that how they're drained? Oh, this is just, yeah, so the statement of the problem starts with a definition. And so the reason that it starts with a definition is so that you don't have to prove that this relation is an equivalence relation. So yes, you are correct. And the statement of the problem, it starts with the definition, and then the first part of the problem is this first proposition, which is that the path components or the path component of x within x is path connected and contained in a connected component, or in the connected component of x. So proof of A. So I just yeah, so okay, so the path component part is easy. So because it's just mostly pushing a definition. So let px be the path component of x, and let y and z be within p of x. Then there exists py and pz, which go from 0, 1 to x, continuous functions such that py of 0 is equal to y, py of 1 is equal to x, pz of 0 is equal to z, and pz of 1 is equal to x. Define then py or p yz is gonna of a point a within the space is just gonna be by definition equal to py of 1 minus 2z, or 1 minus 2a, and this will be for 0 is less than or equal to a, which is less than or equal to 1/2, and then pz of, does that work? Because it'll, at 0, it'll be at 1, so I need it to be, at 0, it'll be at 1, which means I want it to be 2a. Right, so then at 0, it's going to be at 0, so it'll start at y, and then at 1/2, it'll be at 1, so it'll end up at x. And this will be 1 minus 2a, or 1/2 less than or equal to a less than, oh, it's still a, the 2a minus 1 thing. Yeah. Then, so at 1/2, it should be at 1/2, I want it to equal 1. And at 1, I want it to be 0. So I need it to be, so 1/2, I want it to be 1. So I need it to be 2 minus 2a. That doesn't work. Yeah, okay. So 2 minus 2a. So at 1/2, it'll be, it will be 1. So it'll be at x. And then at 1, it will be 0. It'll be at z. So then pyz of 1/2 is equal to py of 1, which is equal to pz of 1, which is equal to x. So by the pasting lemma, pyz from 0, 1 to x is continuous, and thus pyz is a path between y and z. Hence, p of x is connected or path connected. Cool. Yeah, I think that was it's path connected and it's contained in the connected component of x. Okay, so suppose that it's not in the path component of x, or suppose it's not in a connected component of x. Suppose p of x is not contained in the the connected component of x, then there exists well, okay. And p of x is a subset of a such that a has a separation. That is, a is going to be equal to u union v for u and v within the topology on your space. I don't need to specify the space because I'm not moving between spaces. And then so with p of x intersected u non-empty and px intersect v is also non-empty. Yet, I also need to specify that u and v are disjoint. So A has a separation that is A is equal to for u and v within the topology on A. I want the subspace topology. Subspace topology. U intersected V is equal to the empty set, and the path component is also separated between them because it's not in a connected component. Then there exists a Q, 0, 1, a path such that Q of 0 is equal to y, which is within px intersect u, and Q of 1 is equal to z, which is within the path component of x intersected with v. And Q is, or Q of, 0, 1 is the continuous image of a connected set which is just connected. So um, what is it? It's that so Q of 0, 1 intersect with U intersected with um, Q of 0, 1 intersected with V is not empty, but that's a contradiction. Or well, hold up. Yeah. Um, so this is, okay, hold up. Intersect, which is connected. Yeah. So this should be, so this um, should be um, not empty. Do I want to say that? I don't think I want to say that. So it's a connected. Okay, so it's a continuous image of a connected set which is connected. So yet, this is, so acknowledge the contradiction. So yet Q of 0 is within Q of 0, 1 intersect U, and yeah, that's what I'm saying. I'm just doing it in a little bit more um, detail than is usually necessary. So this is within this, and these are subsets of px intersect u, subset of px intersect v, and that's a subset of a intersect u, and u, and so u and v are a separation. Separation. I guess just say a. Say um, just say subset of u. That makes more sense. V, so u and v are a separation of q of 0, 1, and that is a contradiction. It's px must be a subset of the connected component of x. So that finishes prop A. Right? Yes, and then prop B. Prop B is that X is locally connected or locally path connected. If and only if each path component of an open set or of each open set is connected. So proof. The backwards direction is short. So if px is open for every x within x, oh, I don't want to say that. Path component of each open set is. Path component of an open set is just the union of the path. Oh, that's not what I want to say. is connected. So if px is open, that's not what I want to say. Let p u be the path component, or well, yeah, I just need an open set. So let u within tau open and x within u, then oh, say for all, because it's for each path component of the open set is connected. So let u or is open. If and only if each path component of each open set is open. So u is within tau open. Then for every x within u, px is open. And since what am I doing? I just want is open. And oh, this is not hard. X is within u. It's just x is within the intersection, so it's open, and x within u intersect px subset of u is a path connected neighborhood of x in u. So x is locally path connected. Then for the forward direction, suppose it's not open. Then, oh, what is that? That's not what I meant to say. That's not what I meant to write. I said the right thing. I just didn't write the right thing. So suppose p of x, the path component associated with x, is not open. Then px intersects its closure at some point. So there exists p within px, a limit point px, since x is locally path connected for every open set within tau. It probably is, but this might also be an instance of I know how to do it one way and I haven't thought about it the direct way. I don't think so. Locally path connected each, if and only if each path component of each open set is open. Going forward, so it's locally path connected. So for every open set, oh, that doesn't tell me it's open. Locally path connected, the neighborhood that you get out of it is an open set. Let's try it. Might as well, right? So since x is locally path connected, um, for a given x, um, and for every u within tau with x within u, there exists p an open set such that x is within p and p is path connected. Consider then consider px. Well, then this is just the union of all p's, such p's, right? So um, then for every y within, oh, this is weird. For given x within x, for every u within the topology with x within u, there exists a p within the topology such that x is within p and p is path connected. Consider then p is a subset of p is a subset of px. I guess I can make it dependent on u. So yes, okay, so yeah, I'm just starting in the wrong place. You right. So this will be, so let x within, well, each path component of each open set. So let u be open, and x within u, then consider p of x in u. Then if y is within the path component of x, then there exists as so the problem with this is that I don't know that this is open, which means I don't have an open neighborhood about y, which means I can't use the local path connectedness in the sense that I'm using it. open and let X within U, then consider Y is within P of X, then, well, there is a path. Yeah, so there is a path. Um, then there exists Q 0, 1 to U a path. Yeah, we want to show that PX is open, but I don't, so local, but the notion of local path connectedness that I'm using is that for every neighborhood, for every open neighborhood about a point, there exists a path, an open path connected neighborhood about the point that is a subset. That is the goal. And there's the Q, a path. So I'm gonna do this the way that I understand better, because at the end of the day, it doesn't matter if I can prove it in the most efficient way. It just matters that I can prove it. Um, so I'm gonna do it the long way. So suppose that PX is not open. Then there exists P within PX minus PX. Oh, other way around. Limit point of PX. Oh no, it's fine. I appreciate the commentary. But the notion of path connected that I'm used to using requires that in order to find a path connected neighborhood about a point, you need to be in an open neighborhood already. So if you start with an arbitrary point and a path component, because you don't know the path component is empty, is open, you can't jump to there being an open neighborhood about that point in the path component, which was the issue, or why I wasn't seeing it immediately. So I'm just going to go back to this way because this is, to me, this is more straightforward, even though it is indirect. So suppose PX is not open, then there exists a B within the closure minus itself a limit point of the path component, since we're locally path connected, is locally path connected. For every U within the topology there um, with Y within U, or with B within U, there exists P a subset of U open with P or B within P. And P path connected. So as B is within the closure, there exists another element within the intersection of an open set about E first. So this is right for every neighborhood. Let's just remove E. So the deleted neighborhood. So that's what I want to say. So U minus u minus, because it might not intersect at b, right? So u minus b intersect px is not empty. So there exists an A within px intersect u with A not equal to b. So there's a path between them. So there's a path between, so there's a path P from A to B. Ooh. Since, what else do I want to say? So since Px is not open, Px is not the whole space, and Px is a subset of a connected component. So we consider C and P, which is going to be which is a neighborhood of the boundary point. Why do I want that? So the connecting components of X are component of an open set is open. So there's a path P from A to B. Since P of X is not open, oh yeah. So then I don't think I need this. I can connect to the whole neighborhood. For every U within tau, there's a B within open with P within and path connected. So as you have something that's not there, so you have something between the two. And A is within, I want it to be strictly not in P, I think. My brain is fried already. This is great. So there exists an A within PX not equal intersect U, such that um, there exists a path between the two. A to, I guess I don't need U. I can do path connected. So for B within PX, there exists, or I don't know why there's a there exists there. I can do this for P minus B intersect PX does not equal the empty set. So there exists an A within PX intersect P such that there exists P from A to B, but I don't want that either. Because I want A to be within P minus PX. There exists a, yeah, there's a B within PX minus PX. This is very open set. You have a new thing that is within. Why why am I having an issue here? So you have a boundary point and you have an open set about the boundary point, and that open set intersects somewhere in here, but then there's an open set about it. There's more stuff in that open set. So at least that's the idea. I am struggling right now, which is fine. That's part of the process. Uh, part P of X, since X is locally path connected for every U within tau, there with B within U, there exists a P within open with blah 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 and P path connected. So as P is within the closure, this happens. Not equals 0. So okay, so I've got two things going on, right? Um, I have two things that are happening here. So I have stuff in two places. So uh, so since um, px is not open, px does not equal x. I don't want to say that either. I feel like I'm skipping around. So as p is within this thing, that's true. And since p is not within px, this is where the contradiction happens, right? So sort of, because I have something in the closure that I can connect to that isn't actually there. Um, so yeah, okay, so there exists an A within P intersect PX uh, such that there is a path from A to B, but then that means there's a path. There's a path from B to or from X to B to B, as there is one from X to A. So B was in PX, which means that which is the contradiction. That feels weird. PX is not open, and there exists a B that's within the closure, but not PX, a limit point of PX. Since X is locally path connected for every U within the topology with B within U, there exists a path component, or there exists a path connected subset of U open with B within that path component, or that path connected subset. And right, a path connected subset is path connected. So as B is within the closure, that just means that any open set, in this case, the path connected subset, which is open, um, uh, with B deleted from it, intersected with the path component of X, is going to be non-empty. So there exists something that is within the stuff that is path connected and contains B and the path component of X. So there's a path from A to B, and there's the path from X to B. So there is X to A. So B must have been in P of X all along, which is a contradiction. Yeah, this is fine. I think that's okay. Oh, but there's weirdness here, right? Because you can have, if it's not open and it contains its closure, then it's, oh, so it's just closed. Okay, that it's not a contradiction. It's just that it's closed. Then, right, so it's, I guess, suppose, because if it's not, oh, yeah, if it's not open, then it could be closed. So suppose that it was not closed as well. So then this happens. So px must be closed. So there's, yeah, there does not exist px closure minus px. So as px is a subset of px bar, this means that px px is closed. So then, um, so px is a subset of is a strict subset of X because it's not a open set, it's strictly a closed set. So it's a strict subset of X. And there exists C, a connected component of X with px subset of C. Your connected components of your space are, what's the deal with these? So okay, so connected component P of X of C. So consider C union P now, where P is as above, then oh, that doesn't make sense either. This is just wrong. That's where I'm at right now. You have a limit point, and then you show that that limit point cannot be in this. Okay, that's fine. So then P of X must contain all of its limit points, and then that means it's closed. Uh, so I can still look at what happens with a boundary point. That's still fine. But look at what happens with a boundary point. when I look at the complement, still okay. Yeah, this is still fine. So consider then as P is an open neighborhood. A boundary point of Px, we have that P intersect x minus Px does not equal the empty set is open. So C union P is a superset. It's strictly not equal to, is that what I want to say? Okay, pause. What are we doing? It's contained in a connected component of X. Great. So then contained in a connected component of X, uh, consider C union the path component. Well, it's the path, this, oh, okay, okay. So since, um, okay, so we have that this is the case. So this is not going well. It's part of the process, but that's fine. P intersects the complement of Px, which means that it A, there's a path from A to B. It's closed, so Px is the strict subset of X, and it's closed, so its complement is open. The connected component of X with P of X a subset of C, so consider C union P. And as P is an open neighborhood of a boundary point of Px, we have that it intersects the complement of Px. So and P is connected. So P is connected. Okay, so if P intersect C is empty, uh, then there's a contradiction since P is contained in a path. P is contained in a component and P minus Px is a subset of C. So, and P is connected since it is path connected. So that would be a contradiction. So P intersects C must be non-trivial. So P intersects C must be non-trivial. And thus, so there exists And then I guess there's two cases there as well, right? So if px intersect, or px complement intersects C is empty, it's equal to the empty set. This is a contradiction. So px complement intersects C is not empty. So and P intersects px complement as well. So there is something in common with all three of them. P intersect px complement 6C is empty. I feel like I've already. Hmm. I just want to show that the path connected component is larger than what was supposed, right? No, that's not what I want to do. The thing I have written makes no sense to me. So I want to say that C union P is a strictly larger connected component and still path connected, which is or is a strictly larger set than the original connected component, and it's still path connected, which may not be true. Um, so and let's see. Oh, I'm just gonna Google. I'm just gonna do some light Stack Exchange because that's where I'm at right now. So then each component of each open set is open. More general result. All this stuff. Blah blah. No, that's what we want. Fine. What am I proving? What am I trying to prove rather? Each path component of each open set is open. This is locally path connected if and only if each path component of each open set is open. Locally path connected implies that um, that's not what we want. Okay. Going forward, so I have local path connectedness, which I've already used, which is fine. Then Okay, well, X, PX, subset of C. Components are open sets because we're locally path connected. Why is this larger? I don't think it's larger anymore. Open px is not equal to x and px is c, a connecting component of x. Neighborhood. Yeah, I don't think I have this one, which is okay. There's gotta be something somewhere. Where are my books? I guess the silver lining here is that in reality, I would only need to be able to do 9 of the problems. Oh, just basis of locally connected if each, yeah, so X is locally connected if each component of each open set is open. Yeah, so then okay, what about path connected? This is okay. It could be worse. Um, so let me get rid of this. Let's try it one more time. And then I'm gonna have to call it. Because today is not as productive as I wanted it to be, but that's okay. Sometimes it just doesn't like it should. Closed. Just Okay, I'm going back to the trying the direct thing. Even though that made sense to me. It made sense to me a week ago. And now I'm oh, part of the process is feeling stupid. So okay. Each path component of each open set is open. So um, let the X be a path component of an open set. It'll be a path component of X in an open set E within tau, then since locally path connected, there exists P subset of U, an open set such that P is path connected and X is within P. Since X is within P, so P is a subset of PX. X within P, which is a subset of PX. Now let Y within P, then yeah, so it's locally path connected. Open sets of locally path connected sets are locally path connected. That's the other thing. So there's P subset of U and open set such that P is path connected and X is within P. So X is within P is a subset of PX. Now let Y be within PX. Then for every P, there exists a P from a path from Y to Z. As a subset of U. So, okay. Okay. Duh. All right. So from Y to Z, so um, since locally path connected again, there exists a Q subset of U such that I don't want the path to go from P to Z. I just want it to go from, then there exists a P from Y to X. So since we're locally path connected and we're in an open set already, there exists a Q subset of U such that P is within Q within tau and Q path connected. So for every Q within Q, there exists a P from a path from Q to what did I do? I want that to be Q. I want that to be Y. And then for every Q within Q, there's this P from Q to Y, or so, and hence, since equivalence relation, from the equivalence relation above, it's you have something from Y to X as well. So and hence there's a path. There's a path from X to Q within Q for every Q within Q. So P of X is equal to the union of Y within P of X of the Q. Let's see, let's make it dependent on Y. QY, 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 Y is open, and I feel dumb. Okay, cool. Oh gosh. So that was a mess, even though it shouldn't have been. It should have been straightforward. Um, and I just totally messed it up. So I think I really need to do more. I have been, how long have I been going for? How long have I been doing this for? Oh yeah, I need to stop. So yeah. So I guess just reflecting on this being a train wreck today, um, or at least feeling like a train wreck today. Um, when I took my algebra qual, so I took the algebra qual last August as like I took algebra and analysis and I failed algebra miserably, and then analysis I like perfect scored it. Um, but for analysis, like up until the exam, I could the last like 2 weeks before the exam, I felt like I couldn't do it. I like felt like I couldn't do any problems. And then for the algebra qual, I would like wake up and I would take an algebra qual and I would be able to do like of eight or nine of the 12 problems provided, and was able to do that every day up until the qual. And then the qual came, and analysis I did perfect, and algebra I totally screwed up. So it's possible that just me not being able to formulate the idea currently and just butchering it massively for several hours is a good thing. Well, I mean, it's better that's happening now than on the test, which is something I say all the time. But no, yeah, I need to do more stuff, but I don't have much time left today to do that more stuff. So I'm gonna call it quits for the stream today, and I don't know. I'll see how this one went too, since I was just been I asked people and they were like, do it again. So I did it again. It didn't go as well, I think, this time, but I did do more stuff technically because last time I only did one and a half, and this time I did two. Uh, which I really should be able to do more in that amount of time. Um, but yeah, so I'll see how this one goes, and I think I'm gonna do something on Twitch maybe later today if I have the energy. Because it might be like a low energy kind of day, so I don't want to put it up here, but um, yeah. Anyway, oh yeah, prelims are terrible. I know a lot of folks at other schools, they only had like a prelim exam, and it was just one, and it was like a just like basic theory test. Um, and then they have oral arguments. In my program, we have two PhD qualifying exams. So it's like two, but it's like subject specific. And it usually takes people like 2 to 3 years to pass them, which, talking to other grad students, seems insane. But that go to different places, it seems insane. Um, but I am here. I'm doing the thing. It's almost over. Hopefully, I'll either pass it or I'll fail it, and then I will know if I have to do it again or not. And it is what it is. Okay, so now I'm actually gonna go. So see ya, and I will be around the internet somewhere at some point. It's just the summer's been a lot.